Yes, it is time to finish the examples in the textbook. This being a slightly difficult chapter for the student who's doing it for the first time, I shall make it a point to discuss all the solved examples. Now, Klepner has a few things to convey on pages 266 and 267 and 268, and it has got to do with the translation plus rotation of a rolling drum and rolling disc. And let's just go through we went through one method which was a very detailed Newton's law analysis method, which we called it method 1, and we got all the answers. We got the answer for the translational acceleration. I think it was 2 by 3 g sine theta, and I guess we also figured out what is alpha, because mod of A is nothing but mod of R alpha. This was the constraint equation, and in other words, if you know A, you get to know what is R alpha. And in fact, the friction force F could also have been calculated. The equations were sufficient to calculate the friction force that would permit rolling without slipping. So that was what we did last time. Now it's time to have a second look at that problem. Okay, just to tell you what the main formula for us was. The main formula was we first drew the free body diagram, got to know the force external, then we said this is equal to mass into acceleration of the center of mass, and this gave us a set of equations. The other equation is directly using the formula tau cm z is equal to ICM alpha, where alpha is the rotational acceleration as seen by the observer moving along with the center of mass. Now, mind you, this is derived, and this is one of our important formulas. However, for today's approach, we will approach the problem directly from the law, which is tau z is equal to dlz by dt. This will again, I think the author is doing it to consolidate your concept of torque, angular momentum, and the fact that this law leads to the equation tau cm is equal to ICM alpha. And the idea is that to just emphasize that this is a consequence of the law for the rigid body. So that being the objective of this lesson, let's get on with the calculations and see how to do this. So here I have the inclined plane, which is very nicely fixed to the ground. Now the drum is rolling without slipping on this inclined plane. The angle theta is known, and we choose now this as our coordinate system, which is fixed to the inclined plane. No problem there. It's the what's it called? It's an inertial frame. Now here's the free body diagram of the forces on this object. Mind you, it's not a particle, and because of the geometry of the circle, we're pretty sure that the normal force passes through the center. The weight acts through the center, and it's equivalent to mg. And now we've seen this a lot of times, so we'll directly write this angle is theta. That's pretty obvious. Now mg can be broken up into two components, which I shall do it up front so that we'll not waste time later. This is whatever, one of them is mg sine theta and the other is mg cos theta. And now what we realized last time is that there is a friction force acting at this point, which is not equal to mu n, and I think that we're done with the free body diagram. This time we are intending to directly use this equation, and the point we're trying to make is that, look, you'll obviously get the same answer, but the problem helps you to get used to calculating torque, angular momentum, and also feeling good about the fact that it's not any more difficult or easier. So let's calculate torque. This is important. You have to calculate torque about the origin. So let's emphasize what the origin is. Origin is right here, O, and you need this vector RCM for calculating the angular momentum. Now torque is given by, now what you realize here is that I just write it down here, mg cos theta into, let's say the instantaneous position at that moment is x, into x is going to get a negative sign for the torque, okay, plus n x, now plus because it's anti-clockwise with respect to the origin. I think I want to quickly get rid of these two terms as 0. They add up to 0 because n is equal to mg cos theta. Okay, so let's use it up front. Now that's considerably simplifies the torque calculation. Now all that remains is minus mg sine theta into r, okay, where r is the radius of the drum. Just want to emphasize that r is the radius of the drum, and we are done. So please figure this out. It's minus because it is in this, with respect to the origin, it's a clockwise sense. Okay, so this is our first equation. Tau z is equal to minus mg sine theta r. Right, now we'll try to focus on Lz. Okay, so just to not make sure that I don't have to draw the diagram again, I'll now focus on Lz right here. Lz is a formula which is now RCM cross MVCM, right, plus I naught into alpha. Oh, that's a bad mistake. I'm sorry. Omega. I'm sorry. Omega at that instant. I naught into omega, and I naught, or let's write it as ICM. The book says I naught. I'm going to write it as ICM. Obviously, there's no issues here. Now, we did this calculation last time and found out that it's actually equal to minus r, where r is the radius of the drum. One second, minus r into the sign is minus, and into MVCM, and this you can leave it as ICM omega of t. So this was our Lz, and so now let's calculate dLz by dt, which is easy, minus r m ACM plus ICM alpha t. So now equate these two because that's the law. So minus mg sine theta r is equal to minus r m ACM plus ICM alpha, and this is the equation, right? And the other equation you have is I'm just going to take the constraint equation directly. I'm not going to discuss it again. The constraint of rolling without slipping, ACM is equal to minus R alpha, and we're not going to discuss this again. So what I want to tell you is that this equation, let's call it 1, this equation, let's call it 2, has only two unknowns, that is ACM and alpha, and you should calculate ACM and alpha, and obviously you'll get the same answer. And we're nearly done with whatever we want to. I'm not doing the algebra, therefore I can cut short this video, but I hope you're convinced that the equations are equal to the number of unknowns, and you can actually solve and verify that you get the same answer as before. So right, so let me just conclude. What is the point we're trying to make? You can start from, okay, you can start from this. Tau z is equal to dlz by dt, and just make sure that you're calculating tau z and lz with respect to the same origin, which means that you should take your time to make sure you tell everybody what the coordinate system is. Alternatively, you can bypass the whole thing and just use the equation, which is tau z center of mass at any instant of time is equal to I center of mass into alpha at any instant of time. Now this will give you the alpha, which is the rotation is observed from the center of mass, and there is nothing much to do with the translation. It's a straightforward particle mechanics kind of an equation. Oh yes, I don't want to underplay the role of the constraint. It's very important. Please convince yourself that ACM is equal to minus R alpha, where we've taken into account the sign convention. And that, I think, is the end of the problem, but the video has a little bit more to discuss, because we're also talking about what is it that the author would like to convey on page number 268. So I think it's a reasonably standard part of the story. What do you get from the energy method? Now, the energy method, as always, does not tell you anything about time. So time remains a question mark, but might give you the velocity, the correct value of the velocity very quickly. So that being the standard theme, let's also, but what is it that you need now? You need the formula for the energy of what? Of the object. What is the object doing? It's translating, plus it's also rotating, pure rotation. So now the derivation of the formula I'm not giving, but let me just remind you. So let me just write down everything. Energy of a particle, kinetic energy of a particle is half mv square. Now of a rigid body in pure rotation, and this we did a couple of lessons ago, is half I omega square, where I is the moment of inertia, omega t at that instant, whatever velocity at that instant, where I is the moment of inertia about the axis of rotation, whatever it is, it can be anything. But what is it for translation plus rotation? Now I'm going to give you the formula, and I'm not going to bother to prove this. The proof is easy and it is given in Kleppner. I think you should be able to find the proof in the book, and it's a little bit of vector manipulation, which we'll avoid in the video lesson, but it is got a remarkable pattern which is quite easy to remember. So you can think of it as a particle, and that's the translation part of the energy, plus pure rotation about the center of mass, ouch, half I. Now this is important, cm. You can't go around using the formula for any other point. ICM omega at that instant whole square. So this is obviously a very important formula, and we'll use it in the conservation of energy for this particular problem. So what is the problem now? The problem is that the drum is rolling down the inclined plane, and what is the velocity when it reaches the ground? Right. So okay, let's assume that right, this point. Okay, so let's mark this point. So it's come down from this. Let's assume that this is the top of the inclined plane of height h. Right. I think you will be easily convinced that the drop of the height of the center of mass is h. Okay, and that's all you need to know. Right. And this is theta. So the center of mass falls through height h is all you need to note when it goes from the top to the bottom. So what is this is called position A, this is called position B, and the kinetic energy plus the potential energy at A is equal to the kinetic energy plus potential energy at B. And now I'm going to make the most important comment in this part of the lesson. Or can we use this? Is the question. Okay, now this being such an important question, I think I want to go to another slide. So the answer, let me give you the answer up front. You can use conservation of energy because the non-conservative force in this case happens to be friction. Let there be no doubt that friction is present. Okay, let there be no doubt in your mind that there is friction and it is a non-conservative force, but friction does no work, and the reason is the point of contact in ideally the point of contact is at rest. And when you know that when the object is at rest, then the force does no work. So that is one of the conditions where a force does not do any work, when there is no displacement. And since the point of contact is at rest, the friction force does no work, and if the friction force does no work, then for all practical purposes there is no non-conservative force, and working backwards we find that we should just go ahead and use the conservation of energy. So this is the most interesting insight for the student who's looking at it for the first time, and now that you're convinced that we can use this, let's go ahead. Now it's just a matter of a single line. So let me just I know I have told you what is A and what is B, and now it's just for me to write down all the formulae. The kinetic energy at the top is 0, the potential energy at the top is mgh, okay, and this is equal to the kinetic energy at the bottom. I'll just stall for a minute. The potential energy at the bottom, okay, kinetic energy at the bottom is half m vcm square plus half ICM omega square, and the potential energy at the bottom is 0. If I take, let's say I take this as the reference, then the potential energy at the bottom is 0. And with respect to this reference, you know that this is at a height h, and therefore the potential energy is mgh. Okay, so this is a lovely one-liner, and most of the problems in the exams are going to be easy to solve if you just have to remember the formula for ICM. which I'm not going to do in this lesson. What I want you to notice is what are the unknowns in this equation. Now h is known, and it appears as if there are two unknowns, VCM and omega, but they're connected by the so-called constraint equation. Now I'm going to put minus r omega, but as you can see that uh, this is possibly not going to create such a headache because we're going to square both of them, so there is no issue in this particular equation for the sign convention. But nevertheless, now you know that you can find out both VCM and omega, okay, very easily because of the constraint equation. And let me call this equation 2, and this is conservation of energy, which is equation 1. And what is the conclusion of this? We get VCM and omega t in the bat of an eyelid, and that's great. That's the beautiful conservation of energy at work. Well, we don't know what's the time, but that we knew all the time that time is going to remain a question mark. Okay, so that ends all the tricks of the chapter, and it's time now to solve problems and challenge yourselves with lots of problems. You will get plenty of problems from the Rusnick and Halliday and Klepner and Kolenkov. I could solve a few very instructive problems sometime down the line, but it has to come from you. The questions have to come from your side. I'll be happy to discuss quite a few problems here, and many of them actually are very interesting and connected to real life, so it should be a fun experience for you. Good luck, have fun.